Let's write that word down. So please write this one down. The dot product. And you have to use the dot. Right? If you don't use the dot, that bothers me. So this is my propaganda line for this dot product. I love Pythagorean theorem. If anybody asks me in the street that what's your favorite theorem, and then I go Pythagorean theorem. That's it. You know. Pythagorean theorem is for right triangle, correct? Then what about, is there something like that, nice thing like that for general triangle, not for right triangle? That's called law of cosine. And we're going to take a look at that. This law of cosine turned into some very simple machinery that's called dot product. It's very algebraic, no geometry. The dot product is a very simple quantity that you can create that. Then they realized that this is so nice, this all algebraic system that we can measure in celestial system and all that, and we can capture the geometry behind it. So they use it. Riemann and other people use that to something called Riemannian metric and Riemannian geometry. That was the birth of something called non-Euclidean geometry, some geometry that beyond our intuitive level, such as general relativity and quantum mechanics and all that. And they Einstein used the idea of the framework of this non-Euclidean geometry set out by mathematicians. For pure joy, mathematicians did that. This is fun. We're going to just do this one. Doesn't matter it has application or not. But it turned out Einstein thought that's it. That's the way to go. And he believed is not just apparatus. He believed is the way the nature works. And that's how he predicted that this is how much it's going to bend around when you observe this, the star behind the sun and eclipse and all that. It's amazing. Prediction happened to be correct. All right. So it seems like it's an important thing. And here is the law of cosine. I'm going to give it to you and how you turn this one to dot product. Right? Just a moment. Go from here, law of cosine to dot product. All right. Once the law of cosine is arbitrary triangle. An arbitrary triangle, I have one side being A, another side being B, and this side C. No 90 degree, but if I call that one theta, C is called opposite side, right? If theta is a 90 degree, then we have a Pythagorean theorem. If not, how about this one? C squared is A squared plus B squared. Not true for this one, right? So there must be an adjustment term. Right? That is negative 2ab times the cosine theta. That is called what? Law of cosine. All right. So they really liked it because by measuring these distances, we can relate nicely to angle. Another piece of geometry is important is a metric. Metric is a distance. How long is this one? Another important piece in the geometry is this angle. So they thought these nice quantities, the three quantities, tells you the relationship to the angle. So they wanted to actually rearrange it. So it's a 2ab times cosine theta, where the angle is hidden. In this quantity, the angle piece is hidden there. So how do you rearrange it? Is that a squared plus b squared minus c squared? Is that correct? So that's the key here. So we're going to look at it and see what happened with the coordinates, components of the vectors. So here is triangle again, and here's a theta. This time it's going to be vector v. This is going to be vector w, and this is going to have components. Let's say it's O. That's okay, right? So it's going to be x1, y1, z1. This one will be x2, y2, z2. Fair enough? That's happening in three-dimensional space. And in relativity, you push it to T1 and T2. So you go for four-dimensional space. So this allows us to create this angle connection, allows us to create a geometry that you cannot see, but we can define an angle just using the metric system. All right. So what is the right-hand side? How would you write the right-hand side of this one in here to capture that? Right-hand side would be right-hand side here. What's A? What's A here? And would that be vector V, right? But A is not vector itself. What is a good notation for A? This is length of the vector, right? Isn't that right? Plus, what is vector V? B, W, and B. That's the vector W, right? So what is the third one? That's right. Either this direction and that direction doesn't matter. It's going to be the length, right? So can we stick to usual one, V minus W? So V minus W. So the length of V minus W, right? Okay. So that's the right-hand side. Now we have x1, y1, z1, x2, y2, z2. Is that right? Okay, you can plug that in and work really hard and simplify. All right. So that's exercise 2. Simplify. You know, at least there's no square root. Do you see that? We squared it. We squared it, so there's no square root. Simplify the right-hand side. In terms of what? xk, yk, zk. Meaning x1, x2, y1, y2, z1, z2. Right? Pull out your old algebraic skill and simplify this right-hand side. That's your exercise 2. Well, correctly simplified. That's the simplest form you get. Alright? So what now? Any question? By the way, algebraic work. Right. So, left-hand side. I'm gonna look at left-hand side now. That's the right-hand side. Let's come back to left-hand side. So, here, what was left-hand side? Left-hand side, that's right, is 2 times AB, right? What was the vector notation for A and B? It was AB cosine theta So what was 2? A was the length of vector v, right? Times the length of vector w, correct? Times the cosine theta. That was the left-hand side. But it should be equal to the right-hand side. That's how it started, right? But what's the right-hand side? 2 times x1, x2 plus y1, y2 plus z1, z2, right? That's so 2 cancels, leaving the following important. This is something you have to remember now, right? This is something you're going to use a lot. Length of vector v times length of vector w times the cosine theta is equal to x1, x2 plus y1, y2 plus z1, z2. It's equals that. All right? So that's the bottom line. All the calculation out of that, this is a conclusion. We did all that to get this statement right here. Meaning of the statement is the following. If you have coordinate x1, y1, z1, x2, y2, z2, right-hand side is very simple to calculate, right? And left-hand side, this part fairly simple to calculate too. But here is the important part. It tells you the angle. So they use this right-hand side to relate to this angle information. Very simple algebraic quantity, right? To relate to that. So I summarize it like this. I think in the next part. Yeah. Dot product is the right-hand side. And it is kind of algebraically how it encodes. I showed that it encodes the angle information there. So they use that, coordinates and all that to pull out this angle information, and that's how you enter curved space-time and all that. It is using that cosine in various different way. Okay. So let me go ahead and formally define what the dot product is, right? So here's the definition. This gives the motivation, definition. If you have a vector x1, y1, z1, that's a vector notation, right? And here's a big dot right there. And here's a second vector, x2, y2, z2. This is one vector, and that's a second vector, right? And we're defining this dot product to be the right-hand side, which is this one in here. So x1, x2, you multiply the first component, and second component, and third component. Then add them all together. That's the definition of a dot product. What you see in the right-hand side. Why they care about this one? This is the motivation. This pretty simple quantity, encodes this angle information. So that's the definition. You also write it v dot w equals that, x1, y1, z1. All right? Yes. This is an equation. I'm not saying that this equation is equal to that. They just named the right-hand side. That's what it is. They gave the name to the right-hand side. That's why it's called definition. Yeah. If you have two vectors, we're going to name the right-hand side. That name is the dot product, and we use this notation. This one right now doesn't say anything about left-hand side. There will be the theorem that says this dot product is equal to the product of length times the cosine theta. That will be a theorem. All right? So, any other question? So this is a vector, right? That's a vector. But what is this dot product? The dot product is, what is a good word? The dot product is, what's that? Operation. What about this one? If I have actual vector, you do the dot product, and you have a result, right? It's not a new vector. That's my point. It's a scalar, right? It's a scalar. This is a number. x1 times x2 plus y1 times y2 plus z1 times z2. That's a scalar. So if you do a dot product, what do you get? A scalar, not a new vector. That's one thing. Then next section, we learn cross product, right? That cross product gives you a vector. You do that thing, and then you get a new vector. Here, you do that thing, and you get only a number. No, it's not changing angle. It's just It's just what it is. What do you get out of this dot product? You get a number. That's what I'm. Yeah. No, this number meaning that this whole three things multiply together. That's the right question to it. What does this number mean? It means product of three things: length of two vector times the important quantity, cosine theta. That's the meaning of this number. So if you want the cosine theta, you're going to divide that scalar by product of the length of the two vector right here, right? Then you get cosine theta, and then you hit cosine inverse in your calculator. It tells you what that angle is, right? Remember, there was a bearing problem in the homework. So that can be solved in a different way using this machinery. Make sense? All right. So about that. So let me show you how to do this one quickly, and then I'll let you go. All right. You see the vector v1 and v2? And they ask you to calculate dot product v1, v2, right? Then your answer is what kind of object? Number, scalar. So what is v1 here? In component, nice way, is 3, 1, and negative 2, right? And what is v2? 1, negative 1, and 1. So let's see. What is v1 dot v2? What do? You take the first component and multiply, right? So that's 3, right? Make sense? Plus second component multiply, and what is it? Negative 1. Third component multiply to each other, negative 2. So what does that mean? 0. Great. Does anybody happen to know what this means, 0? 90-degree angle. So if you go back, well, if this guy is a 0, v and w, the length is definitely not 0 here, right? If this thing is 0, only chance is that cosine is going to be 0. So what kind of angle is cosine is 0? It turns out 90 degrees is the only angle if you just go around 0 to 360 degree. So this tells you that two vectors are actually in 90-degree relation in three-dimensional space. This is a main application actually that you're going to use a lot in this course. And later there's a projection and all that. The second application kicks in. Make sense? How about B? You think that B is easy enough? 2 times 0 because it's missing there, and so on. Fair enough? That's dot product. That's called dot product. So your answer is mainly perpendicularity is the first application we're going to hit. Second is going to be the angle, and third application is actually important. It is highly motivated from the physics problem. It's called orthogonal projection. These are the three applications. Perpendicularity, what is the angle? And thirdly, projection. So calculation of the work in three-dimensional space. The work calculation you might have seen in physics that heavily uses this machinery, dot product. Yes? That's the, if I have two vectors like this hovering in the three-dimensional space, that angle we're talking about. Between that, that's correct, between that. Not relative to x-axis or anything, between that. Another question is that, how about this angle? I mean, if I happen to look at it here, like, oh, is that my angle? But you always find an angle that is less than 180 degrees. There's a way to do that. That makes sense in three-dimensional space, right? When you're doing that in four-dimensional space, nobody can see this one, so you have to be a little bit more rigorous in terms of orientation. And which one is pointing to what? It has to be a little bit more rigorous machinery you have to go through. But that part's really fun. But we're not doing that here. Just three-dimensional space is enough, and that's the dot product. All right. Have fun over the